Starting this morning, but since there is not many people around and only Germans are here and the taste of Germans is not the best one, let's postpone this after Narseo talk so we can start with something more interesting. So Narseo got his PhD in 2013, if I'm not wrong, from Cambridge. Then he moved to ITSI in Berkeley, doing mobile measurement, instrumenting Android phones and so on. Now he's an assistant professor in Madrid in their network, still he got a double appointment with ITSI, still doing mobile measurement and privacy related stuff and so on and so forth. So welcome to Narseo. You have 1 hour to try to wake up the...
Will do. Okay, thanks for the introduction, Marco. It's actually a great pleasure for me to talk here and describe what we're actually trying to do regarding crowdsourcing mobile measurements and offset traffic. So Steve yesterday talked about the challenges behind our own research efforts, and actually for us, data is kind of our currency. And the problem is that if we're trying to analyze a complex system, like a mobile network, we have to look at each one of those pieces in isolation, and we have to somehow get the right data. So we can use techniques, for instance, like active measurements, and that's basically kind of a nice step because it gives you the ability to perhaps look at the whole internet as, in detail. But if you, for instance, trying to measure something on a mobile system, you have to basically, to get a SIM card, run everything on the phone, and perhaps you will not have access to an ISP in Afghanistan or Iraq. So you're going to be constrained to your own country. We can also use, for instance, static, ISP traffic traces. And the problem behind those is that typically they're not available because they contain a lot of sensitive information. So you have a lot of information from millions of customers. And in addition to that, you don't have the ability to attribute flows to applications. You basically have the aggregate view of volume going to certain places, but you don't really know which application has opened a given connection. In addition to that, you also have to be very careful because when you start looking at those traces, you realize as well that you cannot actually rely on data such as the user agent or pieces of data like the user agent to identify which one is the application, because those are very noisy and somehow they are shared across various applications. Another technique is using, for instance, VPNs and proxies and forward all the traffic to a VPN server where you can actually collect it. But that also has the same limitations as the ISP traces. You don't have the ability to attribute flows to applications. Some research efforts also used VPNs recently to actually penetrate into ISPs in various regions of the world. That has been used, for instance, for censorship or perhaps also to analyze what kind of middle boxes you have in certain ISPs. And the final technique, usually that we use to actually analyze mobile traffic is actually instrumenting phones. So here you basically ask friends to route the devices, and then you can run TCP down on that. But the problem behind it is that you have a lot of, despite the fact that you have a lot of detail, because you can map exactly flows to applications, and you can also have a lot of contextual information from the device, you will not have more than 8 or 10 users because they will not be happy routing their phones and giving away all the traffic to you. So myself, I actually encountered all those issues when I was actually working on with Telefonica people during my PhD. We were the first guys to measure the scale of mobile advertising traffic. But we basically had to look only at the power consumption or the associated power costs of this traffic, and we couldn't go beyond that because we didn't have any sense of application behind it. So that later motivated us to implement something that it's called Real Analyzer. It's a paper at IMC in 2013. And in this paper, we took advantage of Samsung devices because we managed to hack them and get information from the radio interface. So we could correlate applications traffic with the power states of the radio interface. So we could analyze in great detail what was the actual power consumption of a mobile application. And then at Connext, we did the analysis with all this data. So to some extent, we have basically defined a balance between having a scale or having detail on the data. And what I will actually talk about is how to actually take advantage of people to obtain a scale. So first I will describe a project that I joined in 2013, but it has been running since 2010, which is called the Metalizer. So I think Metalizer was one of the first projects that was actually leveraging the concept of crowdsourcing measurements. And that somehow motivate us and actually inspire us to implement the Lumen Privacy Monitor, which is a mobile application that is capable of analyzing and intercepting mobile traffic on user space without actually having to root the phones. And that's giving us a lot of scale. Then I will talk about two preliminary results that we have obtained. One about how third-party tracking services are actually collecting a lot of personal information about us and what kind of organizations are behind it, and also about how mobile applications are securing their TLS flows. I will also mention some of the future works that we're trying to push with the Lumen project, and I will also finally conclude with some notes about the whole system. So I need to acknowledge, or I should acknowledge all the funding bodies behind the project. So this is funded by the NSF, and we have some support from the Data Transparency Lab, which is an initiative pushed by Telefonica and Mozilla to promote online transparency, and also the great research team behind this project, actually from Metalizer and Lumen as well. I cannot actually put everyone here, but those are mainly the guys involved in most of the development efforts. Also, if you have any question at any time, I will be happy to take the question without actually waiting until the end. So Metalizer is a user-centric network troubleshooting tool. So we give users a tool that they can actually run in order to identify misconfigurations on their Wi-Fi access point. Perhaps they have some issues related with IPv6. Maybe their DNS is actually misconfigured. And we are giving them some reports about how to fix it and what are the main problems. So Metalizer is running from the edge of the network. We are actually running those tests from the end user. And we perform in the order of 120 tests in roughly 5 minutes. Anyone, and I'm actually highlighting it in red, can use it because it's a free tool. You can actually go to our website and you can actually run the Java applet, which is supposed to disappear. We are actually working with some people at Untitled on implementing a JavaScript version. You can also run the Command Line client, or you can actually go to Google Play and run the Android version. And I'm saying anyone in theory because it's very hard to convey what actually, for instance, a proxy to a person who doesn't really have any background in networking. So we are trying our best to tell them, yeah, you have some issues with some TCP ports block. You have also some issues with your DNS resolver. And if they want to actually find out more about what's actually going on, then they can click on the question mark and they can have some sort of detailed information about, for instance, what's NAT, or what's a proxy, or why they should care about DNS. And we have actually some interesting experiences. We have seen on Twitter some discussions between one Metalizer user and a T-Mobile representative. So T-Mobile in the US was running a proxy with a vulnerability that has been identified already in 2011. And this is from 2014, I think. So it basically shows that they were not maintaining properly their own online infrastructure. And this user was interacting with them and they shared the results. And then the funny thing was that the user contacted us. And basically he said that I have the senior engineers at T-Mobile using the app now. They're impressed with it. So it was kind of reassuring. It was like a very, it's proof that it's actually being useful for someone. So we are researchers and we lack of good user interface design skills. We cannot really make something beautiful and appealing to users and also useful. So that's perhaps one of the main limitations that we have in this project. So we tried our best to have something easy to use. So the user can click on start, then the tests start running, and then at the end they get the report. And they can navigate through the results, and then they can actually get more information about it. But we also give them the ability to get in touch with us. So we are receiving a lot of emails, mainly from League of Legends players, who are very interested in reducing buffer load because they want to basically have a low latency while they're actually playing with other users. So we have a lot of geek bias in the data set. But even I started in 2013, and actually the project was already quite mature. I was actually responsible for leading the mobile development. And since then, we actually been quite successful in analyzing and obtaining a lot of data from many ISPs. So we don't know how many users have actually run it because we are not collecting any statistics about it. But Google Play says that we have in the order of 69,000 installs as of today. In the database, we have almost 4 million sessions. And as I said, we can measure the internet from the edge of the network, and we have actually almost every single ISP in the world in the dataset. So we have even mobile ISPs in countries like Bhutan or even Afghanistan. As I said, we have a huge big bias because this is actually run by people who are interested in improving network performance for online gaming, and the data is actually very accurate because we are measuring what we actually see. And we can also correlate this with system level information, like for instance, what are the active interfaces. We can guess if the user is actually connecting to the internet through a VPN, or if they're actually connecting over Wi-Fi or over cellular, and we can actually obtain also system level information, like for instance, the root certificate stores on Android for TLS. So the data has been actually very useful for us because we have several papers. For instance, in Mobisis and Hot Middle Box, we managed to publish a paper about the prevalence of proxies on mobile networks. Surprisingly, most of them actually actively modify the traffic that you send through the network. And more surprisingly to us, many of them are actually leaking personal information about you. So if you're connecting through some ISPs, you can actually see that they're injecting headers that can actually contain the value of your phone number, your IMEI, or your IMSI code. And some other ISPs from some European countries are using the X-forwarded 4 header, which is supposed to report the private IP address when you're behind a proxy, to actually report what is your data plan. So they changed the first octet. So instead of saying 10.0.0.1, they say 11 or 12. And this value that they add is actually identifying your data plan. So this is actually used for advertising purposes, because any online server, they can contact those ISPs and get more information about the customer. That's also called the perma cookies, and that became actually quite a hot topic in the US, because the FTC actually showed that this is actually not a good practice. So AT&T and Verizon were injecting this header, which was like a permanent cookie that identifies uniquely the user. AT&T, once the EFF started to report that this practice was actually being in place, they removed it. But Verizon actually kept using it, and it's actually an opt-out feature. So many of the users actually are not aware of these practices. We also analyzed, as I said, the root store on Android devices. So we had access to, in the order, when we did this analysis, to around 20,000 Android devices from various vendors and from various ISPs. We compared the certificates that we were seeing in each one of those devices with those that are actually on Android's source code. And to our surprise, again, we could see that we can find certain vendors, like we can see there Motorola or Samsung devices, adding up to 60 additional certificates to the root store. When we actually analyze if those certificates were of any use to verify any of the main certificates of TLS traffic, we saw that they are actually useless. So we don't really know why they're actually on the devices. Then we also did an analysis, and we clustered them through ISPs. And you can see that, for instance, if you get a mobile device from, let's say, Verizon, or a Motorola device from Verizon, you will likely have those certificates as well. So it's not clear if it's a Motorola practice or if it's an ISP practice. And then last year at IMC, we also used Metalizer to analyze carrier-grade NAT deployment. And we combined Metalizer data with BitTorrent DHT information. So we could actually ask each one of the peers connected on BitTorrent, what are the IP addresses of your peers. And then we could actually identify that they were actually having private IP addresses. By clustering those, we could guess that those ISPs are actually having CGNs, because otherwise you will not have a private IP address when you're actually asking for a peer IP. So we managed to actually identify CGN at a large scale, but the problem is that people don't run BitTorrent on mobile networks. So that's when we actually use the Metalizer data to actually identify whether ISPs are having multiple NATs in cascade, so NAT 444 deployments. And also we identified that many ISPs are having heterogeneous deployments. So some regions are having one behavior and some other regions are having a different behavior. The problem behind the NATs is that there is a good number of ISPs with restrictive port allocations. So they allocate only 512 ports on average to customers. This means that if you're running a peer-to-peer application, you will actually consume most of those ports. And that can actually have a negative impact on your quality of experience. So I will move away from Metalizer now, but basically what this work has actually leveraged was somehow an incentive for us to find a way of capturing as well traffic. As I said at the introduction, we typically do not have access to mobile traffic because ISPs are not happy giving you this type of information. So we were wondering how we can actually implement a service similar to Metalizer that we can put on the App Store that will allow us to actually collect mobile traffic at scale. And that was the origin of the Lumen Privacy Monitor. When we started thinking about this project, we had 4 specific design goals in mind. First, it's that we had to actually do everything on localhost. And that was for the reason of allocating flows to applications. We wanted to have a very accurate fingerprint of how those applications are actually behaving. The second one is that we wanted to do it on user space. Because if you're actually asking people to run rooted devices, then we will have the same limitation with the scale. The third one is that we also wanted to make it useful for users as Metalizer. So we were thinking about what kind of user interface or what kind of application we can implement on top of that. And the fourth one is that we wanted to be ethical. Steve also mentioned that yesterday, and for us it was very important because we are actually having access to all the traffic of the users. So we put a lot of effort in making sure that we were not actually taking more information than the one that we actually need. And we managed to do this by actually using the VPN interface on Android. But instead of using it to actually forward the traffic to a remote machine, we are basically using it to implement a localhost proxy. So all applications traffic is actually forwarded to this default interface, which is the TAN interface. So we are reading raw packets from this. But as we are running on user space and we want to send the traffic to the final destination, we have to use Java regular sockets to open the connection to the final destination. So basically, on the one hand, you're layer 3, and the other one, you're basically reading buffers. So that means that when you're sending traffic out, let's say TCP, you check the first TCP connect, you check the SIM, and then you extract the port and destination IP address from that. You open a socket to this machine, and once the connection is open, you start getting the payload and you put it on the buffer and send it. But the problem is that when you're receiving traffic from the internet, you need to packetize this buffer before sending it to the applications because otherwise the kernel will reject them. So we had to basically implement a full protocol stack on user space. So far we managed to do it efficiently, both in terms of battery consumption and also in terms of throughput. We can provide in the order of 80 megabits per second in user space, which is pretty decent. No application is actually using that. And in addition to that, we are on average consuming between 1% and 2% of your battery. But you have to keep in mind as well that we are also doing out of stuff on top. Because Lumen, the use case we defined for it was basically making a transparency tool so users can know the traffic patterns of their applications, especially when they are actually connecting to third-party tracking services. So we allow users to forward the traffic through a TLS proxy that we also implemented locally on user space. And once we have access to all this payload, we send it to a process that is running on top of this. It's basically like a tap. And then we contextualize all the information that we are seeing on the payload to the raw data we are collecting from the browser. So we use Android permissions to collect, for instance, what are your contacts, what are your messages, what is your IMEI code, And then we do a string matching, and we identify when an application is actually leaking this value and who is actually collecting that information. And this process is also responsible for doing flow assembly. So for instance, most mobile applications are actually GCPing traffic. So we need to wait for the whole payload before actually unzipping it and then analyze it on user space. So as I said, we have to be very careful with the ethical aspects behind it. And that's one of the motivations to do everything on user space. We only send to our server anonymized traffic traces, in which we basically say application X talk to xyz.com over port blah, this is the IP address, and that actually leak the IMEI and so on, but we don't actually get any value about you. So we only care about the type of data that they are leaking. We don't care about what's the value that identifies you as a user. In addition to that, we're also collecting some information like TLS handshakes, because we were very interested in analyzing how applications are actually using TLS. And we will talk about it later as well. Over the time, we were actually discovering that we had to remove certain applications from we had to blacklist certain applications. Because we realized that if you're using a browser, that can actually reveal a lot about you. So at the moment, we are not reporting anything about your browsing history, and we have blacklisted the majority of the most popular browsers. On the other hand, applications like Facebook and Twitter, they can also have different behavior than if they were actually run by, depending on the user that is running it, because some users may actually share some specific domains with news or so and so on, and that can actually identify you a bit. But we're not linking this information to a user profile, and given that this is not as prevalent as in the browser, we are actually kind of safe in that space. So, given that it's running on user space, we can actually use typical distribution channels to publicize and make this tool available for users. So if you go to Google Play, then you can actually search for Lumen Privacy Monitor, and you will find it. And more or less, this is a snapshot of the UI. So here, we have several tabs, and the first one is basically showing an aggregated view of the leaks that we have identified. We have a figure that is actually showing what are the most common trackers across all your applications. So that gives you an idea of the panopticon that they are actually generating about you. And most of them are actually related with Google domains, but surprisingly there are other third-party services like Crashlytics, which is not very well known, which is in the order of 20% of the apps. And then below that we have the full list of leaks that we have identified and the applications that are actually collecting this information. Then you can actually go and check given applications profile. So you can see, for instance, what kind of protocols they use, and also get an estimate of how much traffic they are wasting with third-party services. Surprisingly, it's in the order of 25%. So that means that 25% of your data plan is actually going to third-party services for tracking purposes. And then you can also see the whole list of domains that are being reached by this application. And we highlight those that we know that they are trackers with an eye. And the third view on the right is actually the aggregated view of the whole traffic that we analyze for a given user. So you can actually see here that most of the traffic is HTTPS, but there's still a lot of traffic going over HTTP. And we have analyzed that in the order of 55% of the applications are still having both HTTP and HTTPS. If you want to know more details about the system, I invite you to actually take a look at this paper, which is on arXiv. And I would actually like to move into the ethical discussion. We have a lot of trouble actually publishing this work. And actually, when we submitted it for the first time, one reviewer unblinded himself. He came from one of the main tracking companies. And he said that this work is actually in the intersection of what should not be done and what you must not do. And he thought that we were actually taking advantage of an Android vulnerability. So we have IRB approval. So it means that our ethical committee at Berkeley actually considers this work as a non-human subject research, because we are actually not collecting any personal information. And all we are saying is basically how applications are connecting to the cloud. We are not collecting any personal information. We are not linking this to any user pattern. So we are also stressing in every single submission that the users are actually voluntarily running this application. They have to go to the Google Play Store and they have to find it. And there in the description, we explain what we actually collect, and we have a very detailed privacy policy. And also, when the user is running it for the first time, we explain the data collection. We also point them to the privacy policy and what they will enable if they allow the application to do TLS interception. Still, we have some users that are actually concerned about it. And they go to Google Play and they give you a 1-star rating. And that's basically, it's a very legitimate comment, but it's also, he hasn't realized it's actually an opt-in feature. So it's not mandatory for all users. Perhaps we're thinking that maybe open sourcing it will be one way of fixing it, but we are still not sure if this is actually the right way to do it. Recently, we got overwhelmed because we were not ready for a boost of installs that we got in the last couple of weeks. So until the 30th of May, more or less, we were having 2-3 new users per day. And then suddenly, we wrote an article for an academic journal called The Conversation. And we got a boost of installs because the article was actually talking about the prevalence of third-party tracking services on mobile applications. So here you can see that it got actually captured by big media companies like Scientific American, El País, which is one of the top newspapers in Spain, and also International Business Times. So this translated into a boost of installs that here you can see we reach in the order of 600 users in a single day. And if we correlate this with the number of readers, there's actually a strong correlation. So later on, an Indian newspaper called the Indian Times picked up this news, and they actually talk about it. But actually the funny thing is that the conversation article has a Creative Commons license, but they actually did their own way. And they haven't actually contacted us. But we found out because suddenly we got like 5,000 users coming from India, and we didn't know why. So then doing some research, we found out that actually that was the reason. And here you can see this sign which indicates that we had actually released a new version. The reason for that is that we were not expecting this peak of installs. And we actually entered into panic mode. Why? Because we were not aware of certain devices that we've never heard of. Many people are actually running 4.2 devices with very limited memory. And basically, that translated into out of box, that we had no idea they were actually on the source code. Because we cannot test every single device running Android out there. So just to give you an idea, we have invested in the order of 1.5 years to make to implement the actual tool. And this is a non-stop effort because every single day we're receiving bug reports from devices that we don't really know that they exist. So also because they are running on very old and outdated devices, we're also getting out of memory exceptions. So this is actually one example. FP, does anyone know what's FP?
Floating point.
Pardon?
Floating point.
No, it's called, it's a device called Fairphone. So the idea is that it's used with fair trade products rather than actually abusing developing countries. So this is running only up to Android 4.2. And this device is obviously limited in terms of resources. So this guy was actually complaining that Lumen actually crashed his device. In addition to that, we're also having issues with Samsung devices, because Samsung has rewritten completely the VPN interface, because they have an API or an SDK called Nox, which is a security framework that they actually implement. So we cannot actually make it work for Samsung devices, which is a huge fraction of the mobile users. So as we are getting these things, we either find one of those devices and we test it, or we blacklist it. And sometimes we have to blacklist them because we cannot find those devices to test. And then this actually translates into 4 ratings. And here you can see that there is some devices that don't even report what kind of version they are running. Probably those are custom firmwares, we don't know. And also, you can see that Android 4.2 is actually having the lowest rating. But then, more capable or not so resource-constrained devices are actually having better, we're getting better ratings. So, despite having this panic period, that was actually a very positive thing for us, because up to the 10th of May, we were having in the order of 1,600 users, and that had allowed us to analyze in the order of 4,800 applications. In total, we had 2.5 million flows. And in 2 weeks, we basically grew 3 times the number of users, and we have in the order of 8,000 applications and 5.6 million flows. And that's not including the Indian users that we receive as well. Another interesting thing by running actually locally on the device is that we are capturing not only user stimuli, because if you try those applications on an emulator with a monkey, many of them actually require you to actually log in. And a monkey is not capable of actually entering the right information on the box for logging purposes. So we are actually leveraging this task to the user, or basically outsourcing this task to the users. And in addition to that, we're also capable of analyzing and intercepting network stimuli. So one of the largest American airlines with Wi-Fi on board, if you have the application installed, they report the IMEI to the Wi-Fi access point. And we are capable of actually analyzing those things because we have the real network and the real device. Also, we are capable of analyzing IoT traffic. So we can see how some users running the Samsung Remote TV controller interact with the Samsung TV. So we can see, for instance, applications as well doing home network scans for no reason, or UPnP scans, and so on. So we are using this data as well for different research topics. And the first one is actually analyzing the third-party tracking and advertising ecosystem. So your phone hosts a lot of personal information. And when you install it, you typically think that this information is collected by the application developer. And when you go to Google Play, you check the permissions and you think that this is only information going to the application developer. But there's no information or there's no transparency about all the third-party services that are embedded in the app. So the problem is that there's no way of obtaining this information, because if you go and you use the AppLog Plus application or Ghostery for Android, those are actually browser versions. They are not capable of preventing tracking at the application level. And in addition to that, we also compare the domains that those services are blacklisting, and those are actually web-specific. The majority of the trackers that are found on mobile applications are not actually there. So another interesting finding was that the application permissions do not necessarily protect your privacy. So Google considers the IMEI code, which is a unique identifier of your device, and even the Google ID, which is used for advertising purposes, as very sensitive information, because this can pinpoint you as the right user at a given time. And in addition to that, if the application is uploading this without encryption, as some Chinese browsers are actually doing, that can actually allow any impact observer to monitor your activity in the network. So Android is trying to prevent this by actually encouraging application developers to use TLS, we will talk about it later, but also by asking users to give permission to certain permissions. But this is actually supposedly. Android contains a file. If you have actually the Android SDK installed on your machine, you can actually give it a try. So if you type ADB shell, which is the Android volume bridge, and then you access the shell and you run the command get prop, you will see that you have a lot of unique identifiers there. You have the serial number, you have the MAC address somewhere, not here. You also have the network that you're connecting to. The MAC address is here for Bluetooth. And this is not protected by any permission. And we actually report this to Google as a bug, and they said that this is actually working as it's supposed to work. We don't know why. The funny thing is that we have found instances of third-party tracking services taking this information. So this is actually a bit, let's say, shady. then we also analyze, as I said, how much of this information is actually being sent without encryption. So we filter out the 6 most prevalent unique identifiers, and you can see that many of them are actually, around 4% of the applications are leaking those values without any encryption at all. So the question is, who is actually collecting this information? So for that, we actually we create a graph in which we have applications and domains, and we actually analyze the interactions between them. So we consider that an application, which is actually in the solid black line box here, is talking to a domain, which is, in this case, AccuWeather and Urban Airship. And we try to identify if they are actually third party or not. The basic heuristic is actually if a domain is connected by more than 2 applications, then you can consider it as a third party. But here you can see that the AccuWeather app, both the free and the paid one, are actually talking to AccuWeather. But AccuWeather is also a third-party service for the HTC Sense application. So in order to filter out, basically the first heuristic is actually analyzing the tokens that we have between the package names, which identify the application, and the domains. That basically allows us, for instance, to see that third-party tracking service like Urban Airship is being connected by 3 different applications. So if we run the distribution of how applications connect to third-party services and how many applications are connecting to a given domain, which is what we have here is the app out degree and the domain in degree, we can see that on average, mobile application talks to only 5 domains. And the ones that are actually to the right side, those are actually applications like social media apps or RSS readers, and also email clients, which we are also filtering after realizing this. So you can see as well that around 30% of the domains are actually connected by more than 2 applications. So if you measure how much traffic those account for, it's in the order of 50% of the total traffic. The problem is that if you use this heuristic, then you can actually have false positives, because you can have CDNs, or you can have cloud services that are actually not necessarily tracking. So we have to implement our own method to actually identify or distinguish between those services. The first thing we tried was actually using domain blacklists, and Martin actually used it yesterday in his talk. So we tried to look at EasyList. But again, as I said before, those are actually very web specific. And then we also tried to use URL classification services like McAfee's, and then we realized that those are very vague. So Flurry, which is a tracking service, is actually considered as an internet service. So we cannot rely on any existing data. So what we do is basically we analyze the content of the landing pages of each one of those domains. But many of them are not having any landing page. So those are actually, this is actually a strong signal for tracking, because that means that they are actually APIs. And in addition to that, we also see what kind of personal information they are collecting from the applications. So if they collect any unique identifiers, that's also a strong signal for any tracking activity. So then we rank them by the number of applications that are talking to those domains. And you can see that there is a huge long tail of domains. We have in the order of 700 in the database. But this is actually showing the top 25, I think. And you can see that actually Google's are not actually the most prevalent ones. The first one is Crashlytics, and the second one is the Facebook Graph API. And Facebook is actually providing third-party tracking services for applications, because applications can use this to actually integrate Facebook ads on their own apps, but also for analytic purposes, and also to integrate your app in the social network. So that's actually very common as of today. And then we also crawled the top 1,000 Alexa sites, because we were curious about how many of them were also present on the web. And we found that over 68% of them were actually doing some sort of cross-device tracking. Given that we have the ability to collect data from users, we are not collecting, as I said, any personal information, but we collect 2 pieces of information from the SIM card. One is the MCC code, and the other one is the MNC code. And those identify the operator that is providing you the SIM card. So we didn't want to track users, but we want to find things like this. And here you can see on the left side the top 10 countries in our database when we did this analysis. And on the right side, we use MaxMine to geolocate the services that they are connecting to. So the idea is basically showing how much tracking or personal information is actually flowing from one country to another. Here you can see that the US is obviously dominating this ecosystem, and they have in the order of 30% of the tracking services. But then, to our surprise, China is second with 15% of the domains. And then that also means that you are crossing, your information is actually crossing borders. And you have most of the 5 I's. I don't know if you know what are the 5 I's. These are the countries sharing information with mass surveillance. And you have, for instance, the UK, Canada, and the US, obviously. So your data is actually not safe across borders, and we will be curious to see what happens once the GDPR is in place. And we were also very interested in knowing the prevalence of those trackers across certain applications, types of applications. So here in this figure, we have 3 different categories. The first one is those domains that we know that they are advertising and tracking services. ATSC means advertising and tracking services capable. So we don't know that they are actually, we don't know if their main business is actually tracking users, but they are collecting personal information from other applications. And here you can see that the application categories that are collecting most of the information are actually education apps and games. And in the US as well as in Europe, the regulatory bodies say that you cannot actually track children without parental consent. So that's something that we're actually working on at the moment, which is actually identifying if an application is actually requesting for parental consent or not. And I will show you some slides later about some interesting cases, because the law says that you cannot collect any personal information, for instance, location. And the FTC has fined an advertising company called Inmobi with $2 million because of doing this without consent. But we are finding now ways that applications are actually using to proxy location without actually requesting the location. And I will show you later. So if you go to this website, you can have a what we call the panopticon, which is basically the connections that we have found for the first 1,000 applications and the trackers. Those in the center are the main trackers that we have found back then. It's basically using the first 6 months data. And the blue dots are free applications, green dots are paid, and the other ones are pre-installed services. So if you click on an app, like Cut the Rope, I don't know if you know this game, which is very popular for children, you can see it has a huge number of third-party tracking services. And you can also click through one of those trackers, and then you can see as well how many of other applications are talking to this tracker. Any questions? So now let's move into TLS. So I don't know how many of you know too many details about TLS. I would like to say that I know more than I should. But I'm learning a lot about it after actually starting looking at that. So for opening a TLS flow, the client has to send a client hello. And this client hello goes to the server. And in the client hello, you will find information that can identify how the application developer is opening this flow. So you have information like what kind of cipher suites they are willing to use, they can remove them, they can also use certain extensions to improve security, and so on. So if you go to the Google documentation about how to implement TLS on Android, I actually put this on purpose here, the scroll bar. You will easily take 1 day to read that. And I will tell you that many application developers will not bother to actually check it. So that means that they are using most of them, the default TLS configurations offered by Android. And the problem is that if you are opening a TLS flow and you don't verify that the certificate is actually legitimate using techniques like certificate pinning, or by bundling your own certificate store in the application, rather than using the root store as we saw before, because vendors are actually putting more certificates, so if they want to do TLS interception, they can do it, and you will not find it. Then you actually have to read all this and implement those security aspects, or those security features. So given that we have the ability to be in path, we are collecting the client hello, which is the information that will reveal how the application developer is using TLS. But we're also using the man-in-the-middle proxy to collect TLS alerts whenever an application is actually rejecting your certificate. So we can map the exceptions that we're getting in Java with applications that are actually verifying the certificate. So we know which application is exactly securing TLS. But the first thing is actually finding out how you can passively identify the library that they're using. And I'm sorry for this figure, but it contains a lot of information. But here you can see all the cipher suites that we have identified. And the y-axis you have Android 4x, 5x, 7x, and 3 OpenSSL versions. So what we did was basically fingerprinting those libraries with their default configuration. And the color map is actually showing the order of the cipher suites that are by default being used by those libraries. So by knowing that, then we can check if the application developer is using TLS in a way or not, using the default configuration or in a different way. We have also fingerprint GNU TLS, which is a very common library, and also some Firefox specific TLS libraries. So armed with this information, then we can go on the data and we can see which applications are using the default configuration. And here you can see in this figure the rank. It's a log scale, so it's a bit misleading. But the overall picture is that 85% of the applications use the default TLS configuration on Android. So if you're running an Android 4 device, which is vulnerable, no matter how secure your application and up-to-date your application is, if you're using the default TLS library, your users will be compromised on those devices. And I don't know if you saw the picture of Donald Trump using his Samsung 4 device. So it means that even the head of state of the US can be compromised with this. So what we can see as well is that given that we have the ability to map those observations to applications, we can see that applications with huge developing teams, they can actually secure TLS a bit more. So we can see that Microsoft, Facebook, and those companies are actually making TLS more secure than others. We are also looking at TLS extensions, and I could spend a lot of time here, but I will only talk about ALPN, which is an extension that is used to basically report what application layer protocols you support. So here you can see that still around 23% of the applications are not supporting ALPN. And we can see that from October 2015 until May 2017, ALPN support grew from 20% to 85%. And we have also found interesting cases of applications not using non-standard protocols. And here you can see that Facebook has its own HTTP2 implementation, or its own SPv3 implementation, and also some data synchronization apps have their own open source protocol, which is called BEP. I have to say I've never heard about it before, but we can actually find interesting cases about how applications are actually using TLS. We are also looking for vulnerabilities. So RC4 ciphers have been removed because they are not secure. And here we can see, if we look at the percentage of TLS flow that we have analyzed for each month, we can see that RC4 ciphers have decreased from 75% to 10% more or less. So this is actually a positive step. But this is mainly led by Android removing those ciphers from the default TLS libraries. The shocking bit was that we have still found applications using SSL version 3, which is not secure. And Android doesn't support it. So it means that those application developers are using some TLS libraries in the wrong way. So that actually, some of those applications are having the order of millions, tens of millions of users. We have also found around 20 applications using null ciphers. So it means that they are not using any encryption at all. And we have also found around 300 applications using weak cipher suites. Actually, Quirin talked yesterday about how they were fingerprinting users using client headers the certificates from the clients for push notifications. And we have seen similar things on smart TVs. Because if you're connecting to this smart TV, it has a unique ID on the certificate. The problem is, if you have all these things in place and you don't actually verify those certificates, then your application, your users will be vulnerable to any man-in-the-middle attack. Because you don't actually verify that this certificate is the right one that is supposed to be used for opening the TLS flow. So using the proxy exceptions, we have found that less than 2% of the applications are actually securing the TLS flows. And most of them are actually banking apps, which is kind of expected. But there are around 200 banking apps that do not do it. So the problem is that if you're browsing and there is a man-in-the-middle proxy, you will get a notification on the browser saying that this connection has been compromised, but there's nothing informing you about it when you're actually connecting over and out. So be careful when you use those applications in untrusted networks. So what we are now trying to do with Lumen is basically we are trying to see how different mobile applications are from each other at the traffic level. So the problem is that most people think that Android is just HTTP or HTTPS traffic, but we are seeing applications using peer-to-peer, some applications using proprietary protocols, some applications using ports, especially Chinese apps that are supposed to, I mean, if you go to those reports, they are actually labeled as Trojans. So we're trying to basically do a deep analysis of how applications actually communicate with online services. We're also being able to analyze DNS in the wild, in the sense that we can see how a given ISP is modifying DNS responses for the customers. So this has also implications in terms of surveillance and censorship. We are also now starting to analyze CDN performance, and for that we are also using the Monroe platform to run active measurements. So we can guess, or we can identify which one are the main CDN providers for mobile applications. And then with Monroe, we're running active measurements to see how well they are connected with those ISPs. As I said, we're also collecting out of IoT traffic. And that's actually something that you don't really have the ability to access because this is happening only on the home network. So if you're an ISP, you don't really have access to this. We're actually now trying to build a test bed in which we can actually see how those applications are interacting with smart devices that you put in your home. And we're also trying to leverage a concept that Mark Altman introduced, which is called reactive measurements. So the idea is that you have passive observations, and once you see something, you can trigger some active measurements like Metalizer to find out what's actually going on. So let's say that you see something strange in DNS, maybe you can run a test to see if there's a DNS proxy in the path. Or if you see a certificate, maybe you can run another strange certificate, you can run a test to see if there is a hidden proxy in port 443, and stuff like that. And one of the main development efforts that we are trying to do now is basically related with the children applications. And this is actually done in collaboration with the usable security team at UC Berkeley. So if you go to some Google Play reviews, you will find in some children apps, like this guy saying that the children application had a lot of inappropriate ads. So the funny thing is that we have seen that those applications are actually not honoring users' right to, or users' willingness for anonymity. And this, if you go to the Google Play Android settings, you can opt out for applications leaking your Android ID for advertising purposes. But we're seeing that some third-party tracking services are actually leaking this value even when, when you're saying that you don't want it to be leaked. And I said that you should not collect the location of children without permission. But we are seeing a lot of applications leaking the MAC address of the Wi-Fi access point. So then if you go to Wiggle and you put the MAC address, voila, you're at Dixie. So they are using this as a proxy to get the location of the users without having to request the GPS or any kind of other location. And the other thing that we found interesting is that you can, even in the children app, you can get pornographic advertisements. So that's certainly showing that there is something going wrong. If you want to read something about this specific bit, we have presented it at the IEEE workshop on consumer protection. And here we're describing as well a test bed that we're developing to automatize application execution. So we train a monkey to generate random UI events. we actually compare the monkey efficiency with a real human, and we are pretty decent in terms of application coverage. And the idea is basically making this data available for researchers and also for regulators. And the final thing that we're trying to do, but we are still not sure about the legal implications or the ethical implications as well, is giving users the ability to block certain flows. So we have the ability to be a blocker at the whole system level, rather than just in the browser. So we have tested 3 different methods of locking tracking services. All of them work. But the problem is also whether it's legitimate for us to block this by default, or if we have to give the users the ability to choose what kind of flows they do not want to be leaked, or to be actually reached. So, so far we tried this with the top 20 trackers, and none of them actually complains. Because we're, one of the most advanced methods that we found is basically, well, if the problem is that if you cut the connection by default, the application will think that you are disconnected or that you're in airplane mode. So that doesn't work because they will try to open the connection again. So what we are doing is basically having canned responses. And given that we have the ability to do a man-in-the-middle proxy, we can actually tell the application that, making the application believe that they actually reached the server. Because these connections are only used for uploading data in most cases and not for downloading anything. So it's just a 200 OK, and applications don't typically complain about it. So I will conclude now. I think I did fine time-wise. So I guess that this is mainly a conclusion for students. I think that there is no perfect data set and there's no perfect technique to measure something. So if you don't have the ability to have this data, try to actually implement something that will allow you to have this data. Even if it's very time-consuming, I can tell you that we invested 1.5 years with Lumen. It's actually very worthwhile because we're having a unique data set that it's not available anywhere else. So for that, I have some recommendations. The first one is actually you have to be creative. And it wasn't obvious to actually find out that you can use the VPN permission to intercept traffic on user space. So it took us a lot of testing and a lot of iterations. So try to actually be curious about what you can actually try to do and what is actually interesting you. And do not be afraid of actually hacking. We should not wait for the data to come. And I think that Steve also pitched it very nicely yesterday. Unless you're an industrial research lab, this is not going to happen. So you may need to actually find a way of collecting this data, and one way is actually trying to understand how the systems work. Also try to engage with industry, because they will be able to give you interesting research problems, and they will be able, if you can convince them, they will be also able to give you some data that you will not have access to otherwise. And then feel free to collaborate and ask anyone for a data set. Many of us are actually having limited cycles. When we're planning to do something with the data, we don't have enough cycles for that. So we will be happy to give the data to others and perhaps start a collaboration. And finally, be ethical, because if you're collecting a lot of data, you have to make sure that you're not actually compromising users. So any question?